Imagine you are sitting in a comfortable chair and you reach over to flip on a lamp. The light comes on instantly. You have probably never thought much about what just happened because it seems so obvious, so straightforward. You pressed a switch, electricity flowed through the wire, and the bulb lit up. Simple. But I want you to sit with me for a moment and think about what electricity flowing through a wire actually means. Because the truth is far stranger, far more beautiful, and honestly far more disturbing than what you have been told. Here is the thing that bothered Richard Feynman so much that he spent considerable time thinking about it. If electricity is made of electrons, and electrons are tiny particles that exist inside atoms, then how in the world does electricity move through a wire at all? Think about it. An electron is roughly 1 billion times smaller than the wire you are using. A wire is made of metal atoms, packed tightly together in a crystal lattice structure. An electron trying to move through a wire should be like you trying to walk through a solid wall of people pressed shoulder to shoulder. It should be almost impossible. And yet, electricity flows. Why? The answer is that we have been thinking about this completely wrong. And when you understand what is actually happening, you will realize that electricity does not really flow through wires the way water flows through a pipe. It is something far more mysterious. Let me start with what we know about electrons. An electron has what we call a charge, a negative electrical charge. This is not something the electron does, it is something the electron is. The charge is as fundamental to the electron as the color is to a red ball. Now, here is where things get interesting. When you have a bunch of electrons clustered together or separated from each other, they create an electric field around them. This field is invisible, but it is absolutely real, and it fills the space around the electrons. Every point in space near a charged particle has a field associated with it, and that field has a direction and a strength. Now imagine I have a copper wire, and I connect it to a battery. The moment I do this, something remarkable happens. The electrons inside the copper wire do not suddenly become excited and start racing through the metal like tiny cars on a highway. Instead, the electric field from the battery immediately penetrates into the wire. And I mean immediately, not slowly, not gradually from one end to the other. The field is there, everywhere along the wire, almost instantaneously. And this field is what pushes on the electrons. Here is the crucial part. The electrons in the copper wire do not move very fast at all. This is the disturbing discovery. If you actually calculate the drift velocity of electrons in a typical wire-carrying current, you find that they move at a rate of roughly 1 centimeter per second. 1 centimeter per second. If electricity flowed through the wire the way a car drives down a road, it would take hours for an electron to travel from one end of a living room to the other. And yet, when you flip a light switch, the light comes on in a fraction of a second. How is this possible? The answer lies in understanding that the electricity you are using is not the same as the physical movement of electrons from point A to point B. I know this sounds bizarre, but stay with me. The electricity that powers your lamp is actually a disturbance in the electromagnetic field. It is more like a wave than a flow. And waves can travel very fast, even if the individual particles that make up the wave are moving slowly. Let me give you an analogy that actually works. Imagine a long line of people standing close together, shoulder to shoulder. Now imagine the person at one end pushes the person next to them. That person pushes the next person, and so on down the line. The wave of pushing travels down the line very quickly, even though each individual person moves only a tiny distance. In fact, each person might only move a few inches, but the wave travels all the way down the line in a fraction of a second. This is more like what is happening with electricity in a wire. Now, you might be thinking, but wait, that is still people moving. And you are right to push back. So let me be more precise. When a battery is connected to a wire, the electric field from that battery extends into the space surrounding the wire. This field is not made of anything physical in the way we normally think about physical objects. It is a property of space itself. And this field exerts a force on the electrons in the wire. Here is what actually happens. The electrons in the copper wire are not sitting still. They are always jiggling around, bouncing this way and that due to thermal motion. When the electric field is applied, it does not make them move faster in their random jiggling. Instead, it gives them a slight bias, a gentle nudge in one direction. The electrons still bounce around randomly, but on average, they drift slowly in the direction that the electric field points them. But that slow drift is not what is powering your lamp. What is powering your lamp is the electromagnetic wave that travels along the surface of the wire and through the space surrounding it. This wave carries the energy. The electrons are moving slowly, but the energy they carry is moving at nearly the speed of light. Think of it this way. Imagine a rope lying on the ground stretching for 100 feet. Now imagine you tie a tennis ball to the rope somewhere in the middle. The tennis ball does not roll down the rope. But if you shake one end of the rope, a wave travels down the rope very quickly, and eventually that wave reaches the tennis ball and pushes it. The energy of your shake traveled along the rope quickly, even though the material of the rope barely moved at all. In fact, the rope moves up and down, perpendicular to the direction the wave travels. The wave is a disturbance, not a flow of material. Electricity in a wire is fundamentally similar to this. The electrons are like the material of the rope. They move slowly, mostly just jiggling around with a slight bias in one direction. But the electromagnetic wave, the disturbance in the field, travels much faster and carries the energy. Now here is where Feynman found it really disturbing. The energy does not actually travel through the wire. The energy travels in the space around the wire, in the electromagnetic field surrounding the wire. The wire is almost like a guide. It constrains the field and directs it. But the wire is not the path the energy takes. To understand this better, imagine a wire carrying current. The electric field points along the direction of the wire, pushing the electrons forward. But there is also a magnetic field circling around the wire, perpendicular to it. This magnetic field is created by the moving electrons. Together, the electric field and the magnetic field form an electromagnetic wave that propagates along the outside of the wire, in the space surrounding it. This is where the energy actually lives. You can actually see evidence of this if you know what to look for. If you take a wire carrying current and heat it up, the electrons move faster, but the actual energy delivered to the load, whether it is a light bulb or a heating element, does not increase. What matters is the electromagnetic field configuration. You can also use a superconductor, a wire that conducts electricity with zero resistance. In a superconductor, the electrons can move without any friction at all. And yet, the superconductor does not suddenly deliver infinite power. The power delivered is still limited by the electromagnetic field. This shows that the actual motion of the electrons is not what is delivering the power. Now, I want to make sure you understand that this is not just a philosophical point. This has real, practical consequences. When an engineer designs a circuit, they do not actually think much about the electrons themselves. They think about the voltages and currents, which are manifestations of the electromagnetic fields. And they have learned, through long experience, that these fields are what matter. Here is another surprising consequence. It is possible for current to flow through a wire and for the electrons to move in one direction while the energy is moving in the opposite direction. This seems impossible, but it happens. The direction the electrons drift is not necessarily the direction the energy flows. The energy flows in the direction determined by the cross product of the electric and magnetic fields. This is something Feynman emphasized as particularly strange and wonderful. Let me explain this more carefully. In a wire with current flowing through it, there is an electric field pointing along the wire in the direction the electrons drift. There is also a magnetic field circling the wire. When you take the cross product of these two fields, you get a direction perpendicular to both, which points outward from the wire or inward toward the wire. That is the direction the energy flows, and often, at least some of the energy is flowing inward, coming from the space around the wire and funneling into the wire. This completely inverts our intuitive understanding. We think of energy as something flowing down the wire from the battery to the load. But really, energy from the battery is spreading out into the space around the wire, and the wire is acting like a conductor that siphons that energy into itself. It is like the wire is a straw, and the space around it is the drink. Now, you might wonder how this is even possible. If the energy is coming from the battery, how does it end up surrounding the wire? The answer is that the battery does not push energy down the wire. The battery creates an electric field, and this field exists everywhere connected to the battery. The electric field is not confined to the wire. It extends into all the space around the wire, into the air, everywhere. The battery is, in a sense, creating a field in space, and that field carries the energy outward. The wire is just one path where that field can reach the load. You could actually imagine a thought experiment to make this clearer. Suppose you have a straight wire connected to a battery on one end and a light bulb on the other. Now suppose you twist that wire into a coil or a spiral or any other shape. Does the light bulb get less power? No, it does not. The power delivered stays the same. The electromagnetic field has adjusted itself to the new geometry, but the energy still reaches the load just as effectively. This would be impossible if energy were actually flowing through the wire the way a car drives down a road. But it makes perfect sense if energy is traveling through the field surrounding the wire. In fact, here is something even more striking. You could take that wire out of the way entirely and replace it with a different conductor in a different shape. And as long as the electric and magnetic fields are set up correctly, the energy would still reach the load. The wire is almost incidental. It is the field that matters. Feynman used to emphasize this point in a rather unsettling way. He would say that we have this habit of thinking about electrons as little bullets or marbles, and we imagine them traveling through the wire like traffic on a highway. We have built an entire mental model around this image, but this mental model is completely wrong. The electrons are not passengers traveling to a destination. They are more like the audience in a theater. They are there in the wire, they move a little bit when pushed, But the show, the actual action that matters, is happening all around them in the field. And here is the truly disturbing part. The electrons in the wire at any given moment might have come from an electron cloud somewhere else entirely. In a steady current, there are always electrons in the wire, but the identity of those electrons is constantly changing. Electrons are indistinguishable particles. There is no such thing as the same electron you put in one end of the wire coming out the other. It is like having a line of people passing buckets of water from one end to the other. There is a flow of water and there is a flow of motion down the line. But the water passing through one person's hands at one moment is not the same water that came in at the beginning. When we think about current, we are not really talking about a stream of specific individual electrons traveling from point A to point B. We are talking about a flow pattern, a coordinated motion of a huge number of electrons, most of which are moving slowly, some of which might even be moving backward, but whose collective drift creates a pattern that the field can use to transfer energy. Now, let us think about what this means for understanding circuits. In an ordinary circuit, you have a battery, some wires, and a load like a light bulb. We draw this as a simple diagram: a battery symbol, a line for the wire, a circle for the bulb, and a line connecting them back to the battery. This diagram is useful for predicting behavior, but it is deeply misleading about what is actually happening. What is actually happening is that the battery is creating an electric field in space. This field fills the space around the wires and permeates into the load. The field is not confined to the wire, it is everywhere, and this field is doing the work. It is pushing on the charges in the wire, and it is pushing on the charges in the load. The wire just happens to be a convenient path for the field to influence, because metal is full of free electrons that the field can push on. If you wanted to be really accurate about how electricity works, you would not draw a diagram of wires and batteries. You would draw the electric and magnetic field configuration in space. You would show the field lines emanating from the battery terminals, circulating around the wires, and arriving at the load. You would show how these fields are perpendicular to each other, and how their cross product gives the direction of energy flow. This is a much more accurate picture than the mental image of electrons flowing through wires. But here is what is strange. The circuit diagram, the simplified picture, actually works. It works for predicting voltages, currents, and power. It works for designing circuits. It works for almost everything engineers need to do. And this is because the circuit diagram is a kind of shorthand, a way of representing the field configuration that has proven to be practical and useful. You can design circuit boards, build computers, create entire industries, all without ever really understanding that it is the fields that matter. The diagram is like a map, and while a map is not the territory, it can still tell you how to navigate. This is one of the most interesting aspects of physics. We often develop useful models that hide the deeper reality. We learn the model, we apply it, we become experts with it, and then one day we realize that the model is wrong in a fundamental way. But the model still works, and that is because the model captures some essential pattern or relationship, even if the underlying picture is completely different from what we imagined. Feynman was always bothered by this. He did not want to just use the model. He wanted to understand what was really happening. And what he discovered was that electricity, far from being a simple flow of electrons through wires, is actually a complex interplay of electromagnetic fields, with electrons playing a supporting role rather than being the main actors. Now, I should mention that there is another layer to this story. Electrons are not classical particles. They are quantum mechanical objects. And when you look closely at what is happening in a wire, there are aspects that quantum mechanics must describe. But for the purposes of understanding why electricity does not flow through wires the way water flows through pipes, the classical picture I have described is sufficient. The electromagnetic field picture, with energy traveling through the space around the wires, is correct and far more accurate than the mental image of electrons marching down the wire like tiny soldiers. One more thought experiment to make this really sink in. Imagine you have a very long wire stretching for miles. You connect a battery to one end and a light bulb to the other end. When you connect the battery, how long does it take for the light bulb to turn on? If electricity flowed through the wire like a car drives down a road, you would expect it to take a long time, proportional to the length of the wire. But in reality, the light bulb turns on almost instantly, in a fraction of a second, regardless of how long the wire is. The only delay is due to the speed of light in the material of the wire, which is only slightly slower than the speed of light in vacuum. This is because the information, the establishment of the electromagnetic field configuration, travels at the speed of light. The electrons themselves are barely moving. It is the field that is racing down the wire. And this field is created instantly throughout the entire circuit by the battery, with only the tiny delay associated with the speed of light. Nothing classical, nothing that involves the actual motion of electrons through a distance can explain this. But the electromagnetic field picture explains it perfectly. When Feynman talked about this, he often expressed a kind of amazed puzzlement. Here is something we use every single day, something our entire technological civilization depends on, and yet we have almost completely misunderstood what it is. We think electricity is one thing, but it is really something quite different. And yet, because our simplified model captures the essential relationships, we never noticed. The deep lesson here, I think, is about the nature of understanding itself. True understanding is not just being able to predict outcomes or manipulate a system to do what you want. It is being able to picture what is really happening, to see the underlying mechanism, to understand the why. And sometimes, when you achieve that understanding, you discover that reality is far stranger and far more interesting than the simplified picture suggests. Electricity is not flowing through wires. Energy is radiating outward from the source into the space around the conductors, and the conductors are channeling that energy into the load. The electrons are drifting slowly, almost reluctantly, pushed by the field. But they are not the primary actors in this drama. They are more like the cast and crew of a play, necessary to the production, but not the story itself. The story is the story of the electromagnetic field, invisible but absolutely real, moving through space at the speed of light, transferring energy from the battery to the load. And once you truly understand this, once you have replaced the naive picture of electrons flowing like water with the deeper picture of electromagnetic fields spreading through space, you will never look at electricity the same way again. You will see a lamp cord, and instead of thinking of electrons marching through the copper, you will sense the fields surrounding the cord, invisible but active, carrying energy outward. You will recognize that every circuit is really a system for configuring the electromagnetic field in useful ways. You will understand that the real magic of electricity is not the motion of tiny particles, but the action of invisible fields on those particles. This is what Feynman discovered. This is what he found disturbing, but also wonderful. And it is available to all of us if we slow down enough to truly think about what is happening when we flip a switch and a light comes on.